So why am I here? Um, so I knew John in, I guess, in two ways. So one, I did my PhD at Macquarie. So I was at Macquarie between 2012 and 2016. And in that time, John came and visited almost every year. And among the PhD students, we anticipated his visits with a combination of dread and excitement. So the dread because um, it was a kind of open plan situation. So our desks were in the same space as the discussion area, but that wasn't really a separate room. There were just some pin boards separating us from John. And so it was quite difficult to focus during that time. And in fact, sometimes the PhD students had to flee to the library. But on the other hand, it was also very exciting and we had lots of fun memories. So I didn't collaborate with John myself, but I have fun memories from his visits nevertheless. So, I mean, everybody who knows him, you'd remember that he had a lot of entertaining stories up his sleeves and he would use them at every possible opportunity. Sometimes there were also situations that I found shocking at the time. So, for example, I remember one of my another PhD student at Macquarie had submitted a paper to a journal, you know, for anonymous review. And then John came and said, "Hey, I'm reviewing your paper. I've just been sent your paper to review. How about you explain it on the blackboard right now?" I imagine, you know, it was unexpected, probably slightly stressful for the student. But I'd also like to point out that from the student's point of view at the time, John, so sometimes you get professors visiting that only pay attention to the other professors. John was not like that. He actually took PhD students very seriously and talked to us properly and remembered our names or felt bad about not remembering our names, but that was, yeah, that really stayed with me. And apart from that, on a professional level, John's papers have been very influential on my work. So lots of different topics, and some of them will also come up later in this talk. Okay. So nowadays, machines can do many of the activities that humans used to do as part of their work. So it's fair enough to ask yourself, how far can your job be automated? Now, if you're a scientist, then this question becomes, how far can science be automated? In general, the prospect of being replaced by a machine or robot tends to elicit fear. But this is less the case for scientists, I found, at least anecdotally. So some scientists are not worried about being replaced because they think what they do is too special to be automated. I think this is a difficult view to uphold, in particular because I guess artists also used to think that, and now AI can make kind of interesting art. So some other scientists, including myself, are not worried about science being automated. In fact, I welcome the automation of science, but then the main question becomes, okay, I'm happy for this machine to discover stuff, but how do I then extract information, like that knowledge or that understanding from the machine? And so this paper is like a small step in that direction. So yeah, there's 3 collaborators on this paper, Mario Krenn, Jakob Kottmann, and Alan Asbro-Busek. Mario is now a group leader at the Max Planck Institute in Erlangen. Jakob is, I think, is also a faculty member now in the south of Germany. And Alan Asbro-Busek is well known in Toronto. And I'm now at the Center for Quantum Dynamics at Griffith University. So I do research in photonic quantum information science in different areas. So quantum non-locality, integrated photonics, photonic quantum state generation, and quantum machine learning. And these last 2 topics is what this talk will be about. And of course, John was also very influential on quantum state generation. Okay, so first of all, why would you want to use an automated design approach? Well, photons are a little bit challenging. So first of all, it's already not that easy to have, say, large and well-defined number of photons at a specific point in time, a predetermined point in time. And then also, because of the lack of photon-photon linearities, it's not that straightforward to implement 2 photon gates. So because of that, some tasks that are very easy in other architectures are a bit more difficult with photons. For example, if you're trying to prepare a GHZ state, then is this a pointer? Yeah, ooh, weird pointer. Okay, then that's very easy in the normal circuit picture. You just prepare 3 qubits in the computational 0, apply the Hadamard gate on one of them, and then 2 C-naughts, and you're there. But with photons, it might not be that easy to just have photons whenever you want. And as I mentioned, the C-naught gates are also not as straightforward as in some other platforms. So, okay, that sounds pretty negative. Then why even bother with photons? I mean, photons are indispensable in quantum communication because they travel fast and have low decoherence. They've enabled breakthroughs in quantum foundations, which was also recognized by last year's Nobel Prize in Physics. Photons have been very important in quantum metrology as well, which is, of course, one of the areas that John was very active in, and are also promising for quantum computing. Okay, so for that reason, because photons are important but a bit challenging, there have been other automated design approaches for basically coming up with photonic quantum experiments. So for coming up, say you have a certain objective, you want to achieve something, how do you implement that with a photonic circuit? But previous approaches had a combination of different shortcomings. So some or many were applicable only to a narrow set of problems. Some require a large amount of training data to train the models. It can take a long time to reach solutions. And in general, there's no systematic way of extracting conceptual understanding. Okay, so in this paper, we proposed a new tool, which we call Theseus. And basically, in a nutshell, it's an automated design approach for photonic quantum information experiments. And it uses a combination of continuous and discrete optimization of graphs. And then those graphs are connected or correspond to quantum states and setups. All right, so what can you do with this tool? So it basically allows you to design discrete variable quantum optics experiments. So you could have different objectives in mind. So for example, as I mentioned, it can be quite hard to generate quantum states of interest. And in general, that can't be done deterministically and needs to be done probabilistically. So there's 2 kind of main categories of how state generation is possible, how you identify when you have had a successful event. One is post-selected, and the other one is heralded state generation. In post-selected state generation, you've got the number of photons that you actually want in your target state, and you have to identify a successful generation event by having the photons in certain modes. So you basically need to measure those modes and detect your photons, and thereby you have then also destroyed your state. In heralded state generation, you've got extra modes and extra photons, and you know that you've prepared the state when you detect the extra photons in the extra modes in a particular pattern. So the advantage of heralded state generation is that then you have that state and you can use it forever, whatever you want. So you haven't destroyed it, and you can just, there's no restrictions in how you can mix the modes later on and so on. But you require extra resources. Okay, so then people have different resources in the labs. And so we show that it can be used for probabilistic photon pair sources as well as deterministic single photon sources. You might also be interested in other things, like other objectives other than state generation. We have applied it to the design of linear optical quantum gates, another area that John was active in, and we also discuss other potential applications. Okay, so it's applicable to a relatively wide set of problems. It doesn't require any training data. What about the discovery rates? Okay, so to check that, we basically apply Theseus and compare it with some alternative approaches on tasks that we understand well. Okay, so as the first benchmarking task, we searched for maximally entangled three-party quantum states with up to 10 local dimensions, classified by the Schmidt rank vector. So yeah, and then so we look for states with different Schmidt rank vectors. Now it's known that AT1 can be generated using linear optics, probabilistic photon pair generation, and post-selection. And we compare three methods. So the first is a pure topological circuit search. The second is a reinforcement learning method. And the third one is Theseus. So we can basically compare it on different aspects. The first is how many of the 81 total solutions they find. The topological circuit search found 51 out of the 81. The reinforcement learning algorithm only 17 of the 81. And Theseus found 76 of the 81. So then the other question is, or the other thing you might be interested in is how long it takes these tools to find the solutions. So say the 51, for comparison, the topological, the circuit search took 150 CPU hours, whereas Theseus only took 15 minutes. So that's a speed up by a factor of 600. Then as another benchmarking task, we searched for a qubit Q-trit C0 gate. So here, the qubit is a control, and the Q-trit is the target, and it's heralded. It's a heralded gate. So if the qubit is in the computational 0, then nothing happens to the target. If the qubit is in the computational 1, then in the target, 0 goes to 1, 1 to 2, and 2 to 0. And with previous methods, this took 150,000 CPU hours. With Theseus, it only took 1 CPU second. So that's even more massive speed up. Okay, so this speed up is not just a matter of convenience. So it's not just about hitting enter and then having to twiddle your thumbs less long. It actually means that you can tackle more difficult problems and you can find new solutions to open problems. So we found a high-dimensional GHZ state with probabilistic photon pair sources and post-selection for a case that actually was previously conjectured to be impossible. And I will get back to that example later on. We also found heralded high-dimensional Bell state solution. So for d equals 3, so 3-dimensional Bell means there's 2 particles. Again, with probabilistic photon pair sources, a heralded GHZ state, also with probabilistic photon pair sources. And as I mentioned already, the heralded high-dimensional transformation. Okay, so this basically covers the efficient discovery rates. What about the conceptual understanding? Now, to really explain this, I have to actually go into what Theseus does. So it's basically, it does the design using the framework of weighted colored graphs. And it basically optimizes the graphs with both in terms of continuous and discrete optimization. And those graphs correspond to quantum states and circuits. So basically, you start off with a complete graph, like this. And then the algorithm will spit out a much simpler graph that somehow contains the solution. All right, so first of all, especially given Peter Rowley's talk this morning, just a word of warning, these are not graph states, despite the similar name. So in these graphs here, the vertices in the most direct interpretation correspond to spatial paths of photons. An edge is a probabilistic photon pair, but that does not restrict us to only working with probabilistic photon pairs. The colors are degrees of freedom other than the path. So it could be like polarization, transverse spatial mode, and things like that. And the edge weights are amplitudes, which in the end will translate to coefficient in the terms of the quantum state. So here are some very simple examples. Like subfigure A, we've got two vertices, A and B, connected by a blue edge. So if you post-select for having a photon in path A and B, then this corresponds to, say, a photon pair source where you emit two different paths and both photons have horizontal polarization. Subfigure B is the same, but with vertical polarization because we have a different edge color here. And C, for example, right, would just be one photon is vertically polarized and the other one horizontally. So subfigure F, for example, if we post-select for having a photon in each path, then this corresponds to a polarization entangled photon pair. So either both photons are horizontal or both are vertical. But as I mentioned, this does not restrict us to only working with probabilistic photon pair sources. We can also have deterministic single photon sources by basically still having the same formalism, but just having a virtual vertex, which you can then think of as like a heralding detector, so that you then know you have a photon in the other path. Okay, so then, yep. No, in general, and yeah. So in this example, still I have only two colors, so it's enough to use a two-dimensional degree of freedom, but in general, you can have, higher dimensionalities. So yeah, so now more interesting graphs correspond to more interesting states. So again, for the case of post-selection, you can look at this graph, and to understand what's going on, you need to look at what's called perfect matchings. So perfect matchings are subgraphs, subset of edges which cover each vertex once. So in this example, we've got this red option, so that corresponds to, in this case, 1, 1, 1, 1. And then the blue perfect matching is 0, 0, 0, 0. And so then together, that gives you a GHZ. Okay, as I mentioned, there's a correspondence between the graphs and a quantum state. And basically, depending on what you want to do in your experiment, it allows for post-selection. It also allows for heralding and other things. And a graph corresponds to setups. So depending on what you have available in your lab, it can be implemented in several ways. For example, if you're working with bulk optics or integrated photonics, different degrees of freedom of encoding into the photon and so on. And here in this open source code, we show how to translate from graphs to setups. Okay, so what actually happens in the algorithm? As I mentioned, we start off with a complete graph, and then we end up with a much simpler graph. Here, by the way, Ben is an example of more than two colors. Okay, so basically what we're doing is an optimization of the edge weights in order to minimize a loss function, and that effectively maximizes the fidelity. So for quantum state generation, for example, we can maximize the fidelity with a target state. And then here we have a regularization term, which will drive the solution towards having more zero edges. And then after optimization, we check whether two conditions are satisfied. So the first condition is whether the fidelity is above a certain cutoff that we set, like a certain threshold. So for example, say we're happy with a fidelity of 0.95, then that's what we can set for this F limit. And then the second condition is whether the edge weights are small enough. If both of those things are true, then we have a candidate solution, which we can basically keep, but we can now also try and go for a simpler solution by removing one of the edges and trying to optimize again. So this is why we end up with, a much simpler graph in the end. If both of these conditions are not satisfied, then we check whether we've run out of iterations. If yes, we stop. And if not, then we can try optimizing again with different initial conditions for the edge weights. And in terms of which of the edges to remove in in here. There's different strategies that are possible. So one limiting case would be that you just pick one edge at random, and another limiting case would be that you just pick the edge with the smallest modulus. Okay. So when you end up with a simple graph, the nice thing about it is that you can actually inspect it, understand it, and learn what's going on. So as I mentioned, this is a two-dimensional four-particle GHZ state in post-selection. And it was actually conjectured that it's impossible to have a 3D six-photon GHZ state in post-selection with probabilistic photon pair sources and post-selection. But then when we set Theseus to find a solution, it did find one. So that seemed a bit weird at first. Yep. So then we looked at what's going on. And actually, as I mentioned, you can basically analyze in terms of perfect matchings. And you see these three terms here, which each have one color. So that's terms that we want in a GHZ state. But then we also have this unwanted term. That's a noise term. Now, don't know how well it is. Oh, yeah, it's showing up okay, I guess, in the slide. So basically, we do have a term we don't want, but we can make that term arbitrarily small. So here, for example, I don't know how well you can see it, but there's darker edges and a lighter edge. So each of these desired terms has one light edge, but the unwanted term has three light edges. So that's basically got a smaller probability, and we can make it arbitrarily small and therefore get arbitrarily close to the desired state. But that comes at the cost of lower count rates because each of these desired terms also has one of the light edges. Okay, so why do you want conceptual understanding, apart from the nice feeling, obviously? All right, here's an example of a heralded three-dimensional Bell state. So heralded means in vertices C to H, those are our heralding detectors. And conditional on getting a click in each of them, we want to have produced the 3D Bell state in paths A and B. Now, this also corresponds to a solution for probabilistic photon pair sources. With probabilistic photon pair sources, you generally, it tends to be more likely, so you want 8 photons in this case, but it's more likely that you will be producing 6 photons because they're independent events. So the thing that you want to avoid is that all of your heralding detectors go off, which indicates that you should have a Bell state, but actually you have vacuum in the output modes. That would be bad. And the solution that Theseus has found here does have such a term, but it has it in a pair with a minus sign difference. So there's actually this cancellation of the heralded vacuum. And that's, of course, something that now you can also apply in other heralded state generation tasks. Another reason why you would want conceptual understanding is that, say, okay, great, I've got the solution for the heralded 3D Bell state. That's nice. But what about a 20D Bell state? Now, the complete graph at the beginning for that would have a lot of edges, so it would be a very difficult problem, even, say, on a good computer. But luckily, you don't actually need to do that. So if you have your 3D Bell state solution and you study it and understand it, you can immediately generalize it to arbitrary dimensions. So you don't actually have to run the algorithm anymore. You can just write down the solutions. Okay, so just to summarize, computational approaches allow finding solutions for hard problems. We present this new tool, Theseus, for the computational discovery of quantum information experiments. It's, with it, we have a large speed up compared to the previous methods, but that's not just convenient, it also allows you to tackle more problems. And the key to go beyond an instance of a solution to one problem that you set is going to families of solutions is conceptual understanding. Okay, so that paper that I presented was from 2021, but since then there have also been new developments based on it, including these 2 archive papers from late last year. Yep. And yeah, here are the references again. Yeah, thanks very much.
Okay.
Thanks, Nora. So it seemed to be based on photons there. So can this handle higher order photons?
You mean as noise? Yeah. Yeah. So yes, and in fact, we got a solution at the beginning. So if you look at the first archive version of the paper, there was a solution that I then later looked at and thought, oh, something's not right here with high order terms. And then we explicitly, so when you calculate in the cost function, the fidelity, right? So if you also include up to higher order, you can include the noise in that and then therefore also optimize. So of course, then it takes longer to do that optimization, but yeah, it's possible to take that into account.
So the graph still applies, but now it's
Yeah, so yeah, so the graph applies, but then how you go from the graph to the quantum state produced, in that step, you can say, I will go up to a certain order, and then, yeah. Yeah, well, so the heralding, yeah, sorry, yeah. So the question was, what kind of interactions can be included in this framework? Unitary, or also, it looks like also heralding. Yeah, so if it's heralding as part of the state generation problem, so at the end, that's directly, I mean, as I mentioned there, you designate certain vertices as the heralding detectors. So that's definitely possible. But yes, you can also have these virtual vertices to as early heralding, say, so that you then treat the other output from that virtual photon pair source as just like a deterministic single photon. And I think, so it should also include, yeah, I mean, unitaries for sure, but I think it also includes things like unitaries where you then lose some of the modes as well. Yeah, so what happens then is that you just don't get a good fidelity. So so say you set your threshold to 0.95, then it will not get there. It will start again, it will try again with new initial conditions, not get there, and then it will run out of iterations, and then it will say, okay, give up. But I mean, if it's actually impossible, or otherwise, you also at the beginning make a choice when you start with the complete graph. That sounds like it's a definitive thing, but of course it depends on how many photons do you give it, how many, yeah, and how many paths do you give it. So maybe sometimes you also don't find a solution until you start with a larger graph, and then you find a solution.